Okay, so we're talking about z as a function of both x and y. We looked at domains, we looked at limits. Now it's time to talk about the derivative. In single variable calculus, when we talk about the derivative or the rate of change, what we're describing is as x changes, how is the y value changing? In multivariable calculus, if we're looking at our function z, we're asking ourselves, how does the z value change with respect to both x and y? The problem is that we cannot compute the derivative of both x and y at the same time. So what we need to do when we take derivatives with multivariable functions is we need to take what we call a partial derivative. So a partial derivative just means you're going to choose. Do I want to look at how my function is changing with respect to the x value? Do I want to look at how my function is changing with respect to the y value? So if you want to look at how your function changes with respect to x, the notation is f sub x. And here we're looking at the definition, the limit definition of a derivative at some point ab. So remember this point ab, that's going to be an x and a y value. So if I'm taking the partial derivative with respect to the variable x, then notice in the limit formula, the a value, which is an x value, is what we're adding our h to. The b value, which represents a y value, is remaining fixed. We ignore it. If I wanted to take the derivative with respect to y, so f sub y, at some point, notice that I'm applying the limit formula, the plus h, to the y value. Taking derivatives of multivariable functions is actually very easy. All you do is you treat the variable that you're not using as a constant, and then take the derivative of the variable that you are using. So let's look at this saddle diagram so that we can kind of see what's happening here and why we have to separate our derivatives. Why don't we look at the origin, the point 0, 0. Let's say I wanted to find the derivative of z at the origin. Well, look at this. If I look at the derivative with respect to the variable x, and let's say I'm in the positive x values, and my x values are getting closer and closer and closer and closer to this point 0, 0. So as the x values get closer and closer to the point, the origin, notice the z values are getting smaller and smaller and smaller, so the derivative is negative. Look at what happens when we come in with respect to the y. So let's say I'm approaching the origin and I'm coming along with y values are getting closer and closer and closer to 0. But notice the z values are getting larger. So if I compute the derivative with respect to y, it's actually going to be positive. So I get negative with respect to x, positive with respect to y, which is why we have to do them separately. You can't just get one value for both x and y. Other notations that you may see would be in the next box. If I'm trying to find the derivative with respect to x of some point AB, I can also write it as the derivative with respect to x of AB. I can write it as f sub x of AB. What I would like to bring your attention to is this word symbol here. This symbol is a symbol for partial derivative. So we don't use d. We only use that notation if we have a function of one variable. We use the other symbol, this partial derivative symbol. let's do some examples. We're going to compute the partial derivative with respect to x and y for the given function, and then evaluate it at the point 2, -1. So I'm just going to compute the derivative. If I compute the derivative with respect to x of this function, which is a function of both x and y, again, I'm treating y as a constant, and I'm taking the derivative with respect to x. So x times y is simply y plus 3y squared, and then minus 0. So if I evaluate the partial derivative with respect to x at the point 2, -1, I'm just putting in 2 for x, -1 for y, so I get -1 plus 3, which is equal to 2. Now let's compute the derivative with respect to y of our function. So we're treating x as if it were a constant. The derivative of x times y is simply x plus, now the y is squared, so we bring the 2 in front and it becomes a 6xy, and that's it. So the partial derivative evaluated at 2, -1 is going to be 2 minus 12, or -10. So you see there is a difference. If I compute the derivative with respect to x at that point, I get a positive. If I compute the derivative with respect to y, it's negative. Let's try another one. I'm going to compute the partial derivatives with respect to x and y for my given function, and then evaluate it at the point 1 natural log of 2. Partial derivative with respect to x. Okay, so I have a problem here because this is x times e to the x squared y. I have to use the product rule because I have a product of two functions of x. So if I take the derivative, I'm going to do derivative, keep, plus keep derivative. Derivative of x is 1. And I'm going to keep e to the x squared y plus keep the x. The derivative of e to the x squared y stays the same, times the derivative of the exponent, but I'm taking the derivative of x squared y with respect to the variable x. So it's going to be 2xy. I would like to clean this up just a little bit. So this is going to be e to the x squared y plus 2x squared y times e to the x squared times y. Oftentimes on your MyLab they'll factor. So if I did factor out e to the x squared y, I would get 1 plus 2x squared y in parentheses. So if I evaluate my partial derivative at the point 1 natural log of 2, that's going to be e, x is 1, y is natural log of 2, e to the ln 2, 1 plus 2 ln 2. And then e to the ln 2 is simply 2. So 2 times 1 plus 2 ln 2. And now you could play around with that some more, but I'm fine with just leaving it like that. Let's try the partial derivative of our function with respect to y. The partial derivative, we're treating y as the function x as a constant. So it's going to be x e to the x squared y. And then the derivative of the exponent x squared y is x squared. Or x to the third e to the x squared y. If you're ever unsure about how to do your partial derivatives, if you're treating a variable as if it were a constant, put in a constant, put in 2 or something and see what it looks like. So evaluating this partial derivative at the point 1 common natural log of 2, I get e to the ln of 2, which is simply 2. So if you have functions of more than 2 variables, same rule. Treat all the variables as constants except for the one that you're taking the derivative with respect to. In example 3, I'm supposed to find the partial derivative of f with respect to x and the partial derivative of f with respect to y. My function is sine of 3xy plus x squared z minus z squared. So you notice there's a z in there. So the partial derivative, the partial derivative of my function with respect to x is going to be equal to, I have to use the chain rule, derivative of sine is cosine, inside stays the same, and then take the derivative of the inside. But when I take the derivative of the inside, I'm taking the derivative with respect to the variable x. So it's going to be 3y plus 2xy. And then the minus z squared, the derivative is simply 0. I don't like it on that side because it looks like the 3y plus 2xy is part of the argument of cosine. So I'm actually going to move the 3y plus 2xy in front of the cosine. Okay, and that's it. So if I were to find the partial derivative of my function with respect to y, same thing, chain rule, so it's going to be cosine, inside stays the same, 3xy plus x squared z minus z squared times the derivative of the inside with respect to y. So that's just going to be 3x. X squared z doesn't have a y in it. We're treating it as if it's a constant, so derivative of a constant is simply 0. And again, I'm going to move the 3x to the front of the cosine. So there's no confusion about whether it's part of the argument of cosine or not. All right. So we're going to look at some notation. If you take the partial derivative with respect to y first, and then you take the partial derivative with respect to y again, so here we're just looking at how you would take second partial derivatives, then this is what the notation is. Same as in single variable calculus when you do a second derivative. Or you can use the function notation, partial derivative with respect to y, and with respect to y again, or f sub y sub y. And then we have similar for the partial derivative with respect to x. But now when we take second derivatives, we could take the first derivative with respect to x and the second derivative with respect to y. It's perfectly allowed. So let's say that you did take the derivative with respect to x first, and then you went ahead and took the derivative with respect to y. So this is what our notation would look like. Second derivative, and then look at the partial derivatives. You take the derivative from right to left. You're going in the opposite direction, so with respect to x first, then with respect to y. It's a little bit opposite when you're using the function notation. If you take the partial derivative with respect to x first, that's in the parentheses, take it with respect to y second, that's outside the parentheses. So when you're using the function notation, the order that you're taking the derivative is actually going from left to right. So we're going to, in example 4, we're going to find a bunch of second partial derivatives. We're going to find all of them. So if I wanted to find the partial derivative with respect to x, and I choose to use this notation because it's less writing of my function, and I'm going to leave off the parentheses with the x and y. Then with respect to x, this would be 2y plus 6xy. And I'm also going to go ahead and find the partial derivative with respect to y. With respect to y, it's going to be 2x plus 3x squared minus 15y squared. So when I find the partial derivative with respect to x, and then the second derivative with respect to x, I'm just going to take this derivative with respect to x, and then take the derivative with respect to x again. So it's simply 6y. If I take the partial derivative with respect to y, and then take the derivative with respect to y again, the partial derivative with respect to y is already up here. Now take the derivative with respect to y, and you have a negative 30y. Okay, let's try to take the partial derivative with respect to x first and then with respect to y. So going back to the partial derivative with respect to x, the 2y plus 6xy, if I now decide to take that derivative with respect to y, I end up with just 2 plus 6x. And if I decide to take the partial derivative with respect to y first and then with respect to x, I'm going to look at the partial derivative with respect to y. 2x plus 3x squared minus 15y squared. Now I'm going to take the derivative with respect to x, and I get 2 plus 6x. So notice that these are the same. And with most functions, they will be. The order that you take your second derivative doesn't matter. You could take the derivative with respect to x first, then y, or with respect to y and then x for most functions. At the end of this section, we'll look at a theorem that describes when you can do this. Let's try this with another function. We want to find the 4 second partial derivatives, and then this time we're going to evaluate them at the point natural log of 2 pi over 4. So the partial derivative with respect to the variable x is going to be, remember, sine of y is treated as if it were a constant, like 2. So if I was taking the derivative of 2e to the x, it's just 2e to the x. So this will be e to the x sine y. And then the partial derivative with respect to y, e to the x is treated as if it were a constant. So this is going to be e to the x, derivative of sine y is going to be cosine of y. So now our four partial derivatives, the derivative with respect to x and then x again, is just going to give me e to the x sine y. And then y. The derivative of cosine is negative sine, so this becomes negative e to the x sine y. The partial derivative of x then y. So I'm going to take the partial derivative with respect to x, take that derivative with respect to y, and I should get e to the x cosine y. Now the partial derivative of y and then x, oh, here's the roosters. That should be the same. It's e to the x cosine y. So again, they ended up being the same. Let's go ahead and evaluate these. If I take the partial derivative of x and then x again of natural log 2 comma pi over 4, that's going to be e to the natural log of 2 sine of pi over 4. So that's going to be equal to 2 times sine of pi over 4 is square root 2 over 2. That would just be square root of 2. If I take the partial derivative of y and then y again of natural log of 2 comma pi over 4, that's going to be negative e to the ln of 2 sine of pi over 4, and that's negative 2 times square root 2 over 2. So I get a negative square root of 2. And now notice that these next two partial derivatives, second partial derivatives, are the same. So I'm just going to do one of them. I'll do f of xy of natural log of 2 pi over 4. So that's going to be e to the ln of 2 times cosine of pi over 4, which is 2 times square root 2 over 2, and that just gives me the square root of 2. This is a very short section. We're just introducing how to compute partial derivatives. We'll explore other formulas that we have for derivatives, such as the chain rule, things like that, in the next section. So let's just look at some theorems that may come up. These are just theorems that you can use. So Clause's theorem, which is this first theorem, 14.4, is the important one. The equality of mixed partial derivatives. So if your function is defined on some set in two-dimensional space, so that would be like if you had a z function and we're looking at D being all the points xy in the xy plane. And you look at the partial derivatives of xy and yx. As long as they're continuous, those second partial derivatives are continuous throughout this D, then these will be equal. However, if at any time when you're taking your second derivatives, if they're not continuous at some point, it could happen that they're not the same. So for our purposes, pretty much all of the functions we'll be dealing with, the xy, yx derivatives, partial derivatives, they should be the same. So we also have our definition of differentiability. And remember, when we say derivative, we're looking at the change in our function z. And we can compute that change using our partial derivatives. So this is the same definition of differentiability that we had with single variable calculus. This is just for your information if you want to look through this definition, but we're really not going to use this for anything. Theorem 14.5, this is more usable. So the definition of differentiability is nice to know. But it's not anything that we typically use unless you're going to go on to graduate level mathematics and do proofs with that definition. It's more the theorems that follow, and they follow from the definition of differentiability. So this says that we have a function, it has partial derivatives with respect to x and y, and these derivatives are continuous. So if those partial derivatives are continuous, then the function is differentiable. So these are just theorems that follow from the definition. This is the important one. If a function is differentiable, then we can assume it's continuous, but not the other way around. Continuity does not apply differentiability. So if a function is differentiable, then it's continuous. And that's actually it for this section. Pretty short.